Struggling to scale your IoT infrastructure? Get more performance out of your network today with EMQ. From proof of concept to large-scale deployment, EMQ enables mission-critical IoT solutions at the edge, in the cloud, and across multi-cloud. Learn more at emqx.com.
Welcome to a new episode of the InfoQ podcast. Today, I, Roland Meertens, am going to interview Philip House. In the past, he was a machine learning engineer, and currently he is the chief scientist and co-founder at Based10. He has worked with neural networks for a long time, of which we have an interesting story at the end of the podcast. Because of his work at Based10, Philip and I will talk about how to go from an idea to a deployed model as fast as possible, and how to improve that model afterwards in the most efficient way. We will also discuss how the future of engineering teams looks like, and what the role of data scientists is there. Please enjoy listening to this episode. Welcome, Philip, to the InfoQ podcast. The first topic we want to discuss is going from 0 to 1 and minimizing time to value. What do you mean with that?
I guess what I mean is, how do we make sure that machine learning projects actually leave the notebook, right, or your development environment? So much of what I see, in my work is like these data science projects or machine learning projects that have these like aspirations, and they kind of fall flat for, all sorts of different reasons. And like really what we're trying to do is like get the models into the hands of like the downstream users or the stakeholders as fast as possible.
Yeah, so really trying to get your model into deployment. What kind of tools do you like to use for that, or what kind of tools would you recommend for that?
I keep saying that like we're in the Wild West, and like I keep having to sort of like temperature check, is it still the Wild West? And it turns out from this report last week that I had read, yes, it is. So I think at least in enterprise, most people are doing everything sort of like in-house. They're sort of like building their own tools. I think this is even more the case in startup land. People hiring and building rather than using sort of like that many off-the-shelf tools. I think that there has been like this good ecosystem that's starting to form around getting to value as quickly as possible. Obviously, the company I started with my co-founders is operating in this space. But, there are other great ones, even in the space of just like Jupyter Notebooks. Out of your Jupyter Notebooks, there's like Voila, and then some more like commonly known things like Gradio, Streamlit, Databricks, all the way up to, I guess, the big cloud players like Amazon and others.
Do you remember the name of this report, or can we put it in the show notes somehow?
I think it was just the S&P Global report on MLOps. I'll try and find a link and we can share it.
Yeah, then I'll share it at the end of the podcast or on the InfoQ website. So if we're talking about deploying things, what are good practices then around this process? Are there any engineering best practices at the moment?
Yeah, I think this is like a really interesting area because engineering as a field is, such like a well-established field. Like we really have through the course of time, like iterated on and developed like these best practices for how to sort of like package applications, how to do separations of concerns. And with regards to machine learning, it's kind of like, well, the paradigm is very different, right? So you're going from something which is very deterministic to something is probabilistic. And you're using models in place of sort of deterministic logic. And so some of the patterns aren't quite the same, right? And the actual applications that you're building typically are quite different as well, because you're trying to make predictions around things. And so the types of applications that make predictions are pretty fundamentally different from applications that serve some sort of like very deterministic process. I think there's certainly some similarities, right? I think it's really important to involve like all the stakeholders as early as possible. And this is why sort of like minimizing time to value is such like an important thing to be thinking about as you're doing development in machine learning applications. Because at the end of the day, a machine learning application is just like a means to an end, right? You're building this model because it's going to unlock some value for someone. And usually the stakeholder is not the machine learning engineer or the data scientist. It's somebody who's doing some operationally heavy thing. It might be some like toy app that is like facing consumers. It might be doing recommendations. But, as long as the stakeholders aren't involved, you're really limiting your ability to sort of close that feedback loop between what is the value of this thing and how am I producing this thing. And so, I think this is true in both sort of engineering and machine learning, is like the best products are the ones that have like very clear feedback loops between the development of the product and the actual use of the product. And then, of course, there are other things that we have to sort of think about in the machine learning world around understanding, again, we're training these models on large amounts of data. We don't really have the capacity to sort of look at every data point. We have to look at these things statistically. And because of that, we start to sort of introduce bias and where are we getting bias from? Where is data coming from? And are the models that we're developing to sort of put into sort of these operational flows, are they reinforcing existing structural biases that are inherent in the data? What are the limitations of the models? And so thinking about data is also really important.
Yeah, the one thing which always scares me is that if I have a model and I update it and put it in production again, will it still work? Is everything still the same? Am I still having building on the assumptions I had in the past? Do you have some guardrails there, or are there guardrails necessary when you want to update those machine learning models all the time?
Absolutely. I mean, there's, of course, best practices around just sort of making sure things stay stable as you're updating. But coming from an engineering background, what is the equivalent of doing unit tests for machine learning models? How do we make sure that the model continues to behave in a way at the end of the day, you're optimizing over some metric, whether it be accuracy or something a little bit more exotic. You're optimizing over something. And so you're following that number, you're following the metric. You're not really following sort of what does that actually mean, right? And so it's always good to sort of think about, okay, well, how do I think about what this model should be doing as I iterate on it, and making sure that, hey, can I make sure that if I understand biases in the data, or if I understand where I need the model to perform well, and sort of incorporating those understandings as kind of tests that I do, whether or not they're in an automated way or sort of an ad hoc way. I think obviously automation is the key to sort of doing things in these really closed, tight feedback loops. But if I understand, hey, for this customer segment, this model should be saying this kind of thing, and I can build some statistics around sort of making sure that the model is not moving too much, then I think that's the kind of thing that you got to be thinking about.
Yeah, so I think we now talked a bit about going from 0 and having nothing to 1, where you create some value, and you already mentioned the data a couple of times. So how would you go at extending your data in a valuable way?
I guess fundamentally we have to sort of think about why is data important to machine learning, right? Most machine learning models, they're trained doing some sort of supervised learning. Without sufficient amount of data, you're not going to be able to sort of extract enough signal so that your model is able to sort of perform on something. At the end of the day, data is also changing. So the world around you is changing, and the way that your model needs to perform in that world, it has to also adapt to a changing world. So we got to sort of think about how to evolve. Actually, one sort of little tangent, I was reading the chinchilla paper recently, and what was kind of really interesting is data is now sort of becoming the bottleneck in improvements to a model. So this is one of these things that I think for a very long time we thought, hey, big neural nets, how do we make them better? We add more parameters to the model. We get better performance by creating bigger models. And it turns out that maybe actually data is now becoming the bottleneck. This paper showed that basically that the model size, well, I guess the loss associated with the model is linear in the inverses of both the model size and the size of the data that you use to train it. So there's this trade-off that you have to sort of think about, at least in the forefront of machine learning, where we're starting to get this point where data becomes a bottleneck. So data is obviously very important, right? So then the question is okay, how do we get data? Obviously, there are open data sets, and that usually gives us a great place to start. But, how many domain-specific data sets are there? There's not that many. So we have to sort of think about how do we actually start collecting and generating data? There's a few different ways. I think some of the more novel ways are sort of in synthesizing data. I think that's kind of a whole nother topic. But I think for the majority of people, what we end up doing is getting some unlabeled data and then figuring out, okay, how do we start labeling? And there's this whole ecosystem that exists in the labeling tools and labeling machine learning models. And if we go back to, our initial discussion around sort of hey, 0 to 1, you're trying to build this model. Labeling is this process in which you start with the data, but the end product is both labeled data and also the model that is able to score well on your data set as you're labeling.
I think often it's not only the availability of data. Data is relatively cheap to generate, but having high quality labels with this data and selecting the correct data is, in my opinion, the bigger problem. So how would you select your data depending on what your use case is? Would you have some tips for that?
Yeah, absolutely. So you're kind of presented with a large data set and you're trying to think, okay, well, what is the most efficient way for me to pull signal out of this data set in such a way that I can give my model meaningful information so that it can learn something? And generally, data is somewhat cheap to find. Labels is expensive, right? It's expensive because it's usually very time consuming to label data. Particularly, there's this time quality trade-off. The more time you spend on annotating your data, the higher value it's going to have. But also because it's time, it's also cost, right? It's certainly something that you want to sort of like optimize over. And so like there are lots of interesting ways to sort of think about how should I label in my data. And so let's sort of like just set up like a flow, right? Okay, so I have some unlabeled data and I have some labeling interface. So we can talk about, there's a bunch of different labeling tools out there. You can build your own labeling tools. You can use enterprise labeling tools. And you're effectively trying to figure out, okay, well, what data should I use such that I can create some signal for my model? And then once I have some sort of like initial set of data, I can start training a model. And it's obviously going to have relatively low performance, but I can use that model as part of my data labeling loop. And this is kind of like where the area of like active learning comes in. So the question is, okay, so how do I select the correct data set to label? And so I guess what we're really doing is we're querying our data set somewhat intelligently around where is the data points in this data set such that I'm going to get some useful information. And we can do this, like, so let's say that we have some initial model. What we can do is like start scoring the data on that model and say, hey, what data is this model most uncertain about? So we can sort of start sampling from our data set in terms of like uncertainty. And so through sampling there, we're going to be able to give new labels to the next iteration of the model such that it is now more certain around the areas of uncertainty. Another thing which maybe creates sort of like robustness in your model is like maybe that we have some collection of models that can do some sort of like weak classification on our data. And they are going to have some amount of disagreement. So one model says this, another model says B, A and B. And so I want to form like a committee of my models and say, hey, where is there disagreement amongst you? And then I can select data that way. I mean, obviously, there are lots of different querying strategies that we could use. Like we could think about maybe how do I optimize over like error reduction or how much it's going to impact my model. But I guess the takeaway is that there's lots of intelligent ways for different use cases in data selection.
And you mentioned initial models. What is your opinion on those large-scale foundational models which you see nowadays, or using pre-trained models? So with foundational models, I mean like GPT-3 or CLIP.
Yeah. So I think that there's a cohort of people in the world that are going to say that basically it's foundational models or nothing, right? It's kind of like foundational models will eat machine learning and it's just a matter of time.
Yeah, it's general AI.
Yeah, something like that. I mean, I think to the labeling example, it's like, yeah, these foundational models are incredibly good. Like think of something like CLIP, that is this model which is conditioned over text and images. And let's say I have some image classification task. I can use CLIP as a way to bootstrap my labeling process. And then as I add more and more labels, I can start thinking about, okay, I can not just use it to bootstrap my labeling process, I can also use it to bootstrap my model. And I can start fine-tuning one of these foundational models on my specific task. And I think that there is like a lot of value in these foundational models in terms of their ability to sort of like generalize, and particularly generalize when you are able to do some fine-tuning on them. But I think it raises like this very important question because like, you know, you mentioned GPT-3, this is a closed source model, right? And so it's kind of worrying to live in this world where few very large companies control the keys to these foundational models. And like that's why I think the open science initiatives that are happening in the machine learning world, like, you know, Big Science, I think as of time of recording this, I'm not sure when this comes out, but like, you know, a couple of days ago, the Stable Diffusion model came out, which is like super exciting, which is essentially like a DALL-E type model that does image generation based off text, which does amazing high quality images from text. Yeah, certainly like the openness around foundational models is going to be sort of like pretty fundamental to making sure that machine learning is a democratized thing.
And are you at all concerned about how well models generalize, or what kind of model psychology is going on, or what problems a model can solve, or what abstractions it learns?
Yes. I mean, like just going back to stable diffusion, of course, like obviously the first thing I did when I see this model get released, I pulled down a version. And this is great because this is a model that is able to run on consumer hardware. And like the classic thing that you do with this model is you say astronaut riding horse, right? And then, of course, it produces this beautiful image of an astronaut riding a horse. And if you stop to think about it a little bit and look at the image, it's like, oh, it's really learned so much. You know, there's nothing in reality which actually looks like this. But I can ask for a photograph of an astronaut riding a horse and it's able to produce one for me. It's not just the astronaut riding a horse. It understands the context around sort of like there's space in the background and understands that astronauts happen to live in space. And you're like, oh, wow, it's really understood like my prompt in a way that it's filled in all the gaps that I've left. And then, of course, you write horse riding astronaut. And you know what the response is from the model is an astronaut riding a horse. And so clearly that there is some limitation in the model because it's understood the relationship between all these things in the data distributions that it's been trained on. And it's able to sort of fill in the gaps and sort of extrapolate around sort of like somewhat plausible things. But when you sort of ask it to do something that seems really implausible, it's so far out of its model of the world that it just defaults back to like, oh, you must have met this, right? You must have met the inverse because there's no such thing as a horse that rides an astronaut.
Oh, interesting. I'm always super amazed at how if you ask the model, for example, to draw an elephant with a snorkel, it actually understands that elephants might breathe like not through their mouth, so it draws the snorkel at a different place you would expect. So it has a really good understanding of where to put things you would put on humans, but put on animals. So I'm always very amazed at how it gets more concepts than I could have programmed myself manually.
I think it's amazing how well these things tend to generalize in directions that kind of make sense, right? And I kind of feel as though this is where a lot of the open questions exist. It's just like, where are these boundaries around generalization, right? And I don't think that the tools really exist today that really give us like some systematic way of sort of like encapsulating, hey, what is it that this model has learned? And very often upon this sort of like the trainers of the model, the machine learning experts, to sort of maybe know enough about the distributions of the data and about the architecture of the model to sort of like start poking it in the places where maybe these limitations might exist. And this is where, you know, bias in machine learning is really frightening because you just really don't know, like, how do I understand what's being baked into this model in a way that is transparent to me as the creator of the thing?
Yeah, the bias is very real. I think yesterday I tried to generate a picture of a really good wolf, like a really friendly wolf meeting the Pope, but all the images it generated were of an evil-looking wolf, which I guess is the bias on the internet towards wolves. And you don't realize it until you start generating these images that you see this implicit bias from the training data come through your results in ways you don't expect.
And I think this is kind of where AI starts to, not just on the data bias in the technical sense, but also in the ethical sense, to really start thinking about how these things get used. And, you know, obviously the world's changing very rapidly in this regard and people are trying to understand these things as best they can. But I think it just sort of like underscores the need to involve the stakeholders in the sort of the downstream tasks of like how you're using these models. I think data scientists and machine learning engineers, like they're very good at understanding and solving technical problems. And they've basically mapped something from the real world into something which is inherently data set centric. And there's this translation back to the real world that I think it really needs to be done in tandem with people who understand how this model is going to be used and how it's going to impact people.
Yeah, so if we're talking about that, so we already now talked about minimizing the time to value and extending your data in a valuable way. So who would you have in a team if you are setting this up at a company?
I think this is like a really big question. And I think it depends on how like end to end you want to sort of like talk about this. I think machine learning projects start at problem definition to problem solution. And problem definition and solution generally operate in the real world. And the job of the data scientist is usually in sort of like the data domain. So everything gets mapped down to this domain, which is very technical and mathematical. And there are all sorts of requirements that you have on the team there in terms of data scientist. Data scientist means so many different things, right? It's kind of like the title that means everything from doing ETL to feature engineering to training models to deploying models to monitoring models. Also includes things that sort of like happening orthogonally, maybe like business analyst. But I think on the machine learning side of things, there's a lot of engineering problems that's starting to get specialized in terms of on the data side of things, understanding how to operate over large data sets, data engineering. Then you have your data scientist who's maybe doing feature engineering and model architecture design and training these things. And then it's like, okay, well, now you have this model. How do I actually operationalize this in a way that is now tapping into sort of like the inherent value of the thing? And so how do you tap into the value? You basically make it available to be used somewhere. And so there's kind of like traditional sort of like DevOps, ML ops kind of like engineering that's required. And then of course, like, you know, at the end of the day, like these things end up in products. So there's product engineering, there's design. And then surrounding all of this thing is like the domain in which you're operating. So they're the domain experts. And so there's all sorts of like considerations in terms of the team. And what tends to happen more often than not is in companies that are smaller than Google and Microsoft and Uber, a lot of people get tasked with wearing a lot of hats. And so I think when it comes to building a team, you have to sort of think about how can I do more with less? And I think it becomes a question around what am I good at and what are the battles that I want to pick? Do I want to be an infrastructure engineer or do I want to train models? And so if I don't want to be an infrastructure engineer and learn Kubernetes and about scalability and reliability, all these kinds of things, like what tools exist that are going to be able to support me for like the size and the stage of the company that I'm in? Particularly in smaller companies, there's a huge number of skills that are required to sort of like extract value out of a machine learning project. And this is why I love to operate in this space, because I think machine learning has got so much potential for impact in the world. And it's about finding how do you give people like superpowers and allow them to specialize in the things that create the most value where humans need to be involved, and how to sort of allow them to extract that value in the real world.
If you're just having a smaller company, how would you deal with lacking skills or responsibilities? Can this be filled with tools or education?
It's a combination of tools and education. I think one of the great things about the machine learning world is like it's very exciting, and you know, exciting things tend to attract lots of interest. And with lots of interest, lots of tools proliferate. And so I think that there's certainly no lack of tools. I think what's clear to me is that, like, you know, the space is evolving so quickly and the needs are evolving so quickly and what's possible is evolving so quickly that the tools are always playing in this sort of feedback loop with like research tooling and people of like, what are the right tools for the right job at the right time? And I think that it hasn't settled. There's no stable place in this machine learning world. And I think that there are different tools that are really useful for different use cases, and lots of the time that different tools for different sizes and stages of your machine learning journey. And there are like fantastic educational resources out there. Of course, you know, I particularly like blogs because I feel as though they're really good at distilling the core concepts, but also sort of doing exposition and some demonstration of things. And they usually end up leading you to the right sort of set of tools. What becomes really hard is sort of understanding the trade-offs and making sure that you straddle the build versus buy, hire versus buy kind of line effectively. And I don't think that there is like a solution to this. I think it's about just kind of like staying attuned to what's happening in the world.
And if we're coming back to all the new AI technologies, do you think that there will be new disciplines showing up in the near future to extend on the data scientist role to be more specialist?
Yeah, absolutely. I mean, I think one of the good things that's happened over the last few years is that specializations are really starting to solidify around data engineering, model development, ML engineers, ML ops engineers. But I think going back to our conversation around some of these foundational models, like if you are to say that like these things are really going to play a pretty central role in machine learning, then what kind of roles might end up appearing here? Because, you know, model fine-tuning of a foundational model is a very different kind of responsibility, maybe technically lighter, but maybe requires more sort of domain knowledge. And so it's this kind of like hybrid data scientist, domain expert kind of position. And I think tooling will exist to sort of like really give people the ability to do fine tuning on these foundational models. And so I think maybe there is an opportunity for sort of like the model fine tuner thing. I think going back to stable diffusion or DALL-E type models, like I think astronaut riding horse, you get an astronaut riding a horse. Horse riding astronaut, you get an astronaut riding a horse. But if you prompt the model in the right way, if you say maybe not horse riding astronaut, but rather horse sitting on back of astronaut, and maybe with additional prompting, you might actually be able to get what you need to do. But that really requires a deep understanding of the model and how the model is thinking about the world. And so I think what's kind of like really interesting is this idea that like, these models are pretty opaque. And so I think you mentioned like model psychology earlier, like is there opportunity for like model psychologists? Like who's going to be the Sigmund Freud of machine learning and sort of develop this theory about how do I psychoanalyze a model and understand what is this model thinking about the world? What is its opinion and abstractions that it's learned around the world of the data that it's built?
And maybe even know that if you want to have specific outputs, you should rather go for one model rather than another. I really like your example of the horse sitting on the back of an astronaut, because I just typed it into DALL-E, and even the OpenAI website also can't create horses on the back of astronauts. So listeners can send us a message if they manage to create one. As a last thing, you mentioned that you have extensive experience in neural networks and horses. Can you explain how you started working with neural networks?
This is a bit of a stretch, but I grew up, my dad was, let's say, an avid investor at the horse track. And so one of the things I remember as a child back in the early 90s was we'd go to the horse track and there'd be a little rating given to each horse and provide some number. And I learned that NN stood for neural network. And so these people were building these MLPs to basically score horses. And so this is like a very early exposure to neural networks. And so I did a little digging as a kid, and obviously it was kind of over my head. But as I sort of like progressed through teenage years and into university, I was getting exposed to these things again in the context of mathematical modeling. And this is kind of like how I entered the world of machine learning, is initially with the Netflix prize and realizing that, hey, everyone's just doing SVD to win this $1 million prize. I'm like, hey, like maybe mathematics is like useful outside of this world. And yeah, I made this transition into machine learning and haven't looked back. Neural networks.
Fantastic. I really love the story. So yeah, thank you for being on the podcast.
Thanks for having me. I mean, it was a real pleasure.
Thank you very much for listening to this podcast. And thank you, Philip, for joining the podcast. If you look at the show notes on InfoQ.com, you will find more information about the chinchilla paper we talked about and the S&P Global Market Intelligence Report. Thanks again for listening to the InfoQ podcast.